Okay, so this was the program, and I wrote everything that the program is using in the same file so that it's self-contained, so we can analyze exactly what's going on. So this is the main sorting function, sort. But now I gave it the comparison function as an argument, and so to remind you very quickly that the empty list is already sorted, and to sort a non-empty list, we take its head, and then we take all the elements that are smaller than the head, and we put it in front, sorted, and all the elements that are bigger than the head, we sort them, and then we put them after the head. And we needed, to do that, we needed this helper function, which is very helpful indeed, called filter, that selects all the elements in a list with a certain property. And finally, to have a completely self-contained program, I wrote the function append here. I re-implemented it so that we have it, we can see it. And also the comparison function that we're going to use is just going to do the difference. So we're going to do x minus y, and then we compare it with 0 to see if it was greater than or equal versus, less than or equal versus greater than. Okay? So this is completely self-contained. And what does benchmarking mean? I wrote here another little helper function, and this is exactly the kind of function that I use in test harness for your assignments. And this generates a random list of integers with which I'm going to use for input. So I give it the length of the list, and this generates a random list of that length. And now I just call sort on that list. Okay? Now, how do I see how do I benchmark my program? And most programming languages have some kind of built-in facility for benchmarking, which is usually called profiling. And that's also called for OCaml. So profiling is a way of instrumenting the program. Instrumenting means adding stuff to it. Instrumenting your program so it keeps track of various resource usage. And in the case of OCaml, the profiling compiler is called OCaml CP. And if you give it the option -p, what it's going to do is going to instrument your program with profiling information. So what I'm going to do to profile the program, first I'm going to remove some junk that's in the current directory. This is where the database of information is stored, but if I want to profile it several times, I want to have a fresh database. So first I remove it. rm is the Unix command that removes the file. Then I am creating a profile version of my program. Then I am running it, and then this other program called OCaml prof that comes with OCaml, what it's going to do is going to interpret the profiling information for me. So to begin with, I'm going to run it on a list of 10 elements. So I say create a random list of 10 elements, sort it, and then let's see the profiling information. So I need to execute this. And here at the bottom now, this is the output of my command. And you can see a copy of my program. This is what OCaml prof produces. And you see a copy of the program with all these comments that have numbers in them. And that number tells you how many times that bit of code was executed. So this tells me that the whole compare function was called 44 times. So in order to sort my 10 elements array, I had to call compare 4 times. I have to call append 43 times. I had to call filter 64 times. And I have to call sort 21 times. And even more, you get more detailed information. You can see how many times the base case was called and how many times the inductive case was called. So what I'm going to do, I'm going to take this information and put it in a spreadsheet. Actually, I put it ahead of time. I'm going to put the compares, the appends, the filters, and the sorts. But it's a bit, I'm not going to do it live because it's boring and time consuming, but then I can just put 100, I save the program, and I execute again the profiling, and now here on the bottom you see the new data. If I sort now a random list of 100 elements, I had to do 1300 compares, I had to do 600 appends, I had to do 1542 filters, 201 sorts. And if I put 1000, then you can see that the numbers grow quite quickly. For 1000 elements, I needed 27,000 compares and 29,000 executions of filter. And now I have to interpret this data somehow. Yeah, I have to put it in a way that I can see, first of all, what's going on. So I put it in a table like this. So what do we have in this table here? So I put various sizes. I put 10, 20, 30, and then I jumped to 100, 1,000, 10,000, and 20,000 elements. And you can see how they compare. And here I plotted a graph of how the number of executions of the various functions grows relative to the size of the input. So you can see that how compares and appends grow very fast, the sorts don't grow very fast. And this is not very informative at the level of detail, but there's one thing in this graph that is actually interesting, and it's the inflection of this line. You can see that the time of execution grows faster than the size of the input. Now, for those of you who did some kind of A-level math, that means this function grows faster than a linear function. So a linear function would be a straight line. Something that grows slower than the linear line would be very nice. It's something like a logarithm. Something that grows faster, the faster it grows, the worse it is. So a polynomial would grow faster, but an exponential would grow even faster. And the one thing that we really want to not have when we do a program is we don't want to have exponential behavior. If you have an exponential program, it means it's as bad as trying all the combinations and selecting the answer. Because that is exponential behavior. Counting the number of combinations is an exponential number it's exponential in the size of the input. So what we want, the only thing we're going to make sure here is that we don't have exponential behavior. And just looking at it here, it's quite clear that it's not linear, it's worse than linear, but it's hard to tell what it is. So in order to make sure, we're going to put the same data in a different format. So here, it's called the log scale format. So I'm going to keep the size of the input in the same format, but now for the number of times it executes, I'm going to apply the logarithm to it. Yeah? And that's called the log scale. And the nice thing about the log scale is that if we had exponential behavior on a log scale diagram, it would look like a straight line. because the logarithm of the exponential is linear. Yeah, so it's a little bit of a math trick. It doesn't really, you don't have to really understand why, but you just have to understand these two things, that it's in order to detect exponential behavior, but just to eyeball it, because we have data, we don't have formulas, we just collect execution data. So we put it, first we put it on this normal scale, and we see that it's superlinear, so it's faster than linear. Then we put it on a logarithmic scale, and we can see it's actually, happily, it's sub-exponential, because you see, this goes like this. So it grows slower. If any straight line that I would put here, even though at some point this might grow faster than it, eventually it seems to flatten out and grow slower than any line of fixed slope. So by comparison, here you have the exponential function. So you can see how it compares with, for example, something that goes quickly, like the appends. So you see it's 3 versus 0.1, 4, 0.2, 5, 0.3, 6, 1. So up to this point, you have more than exponential appends. But for the size of 1000, you have 9 point something versus 10, 13 versus 100, 14 versus 200. So you can see it's actually growing far less than the exponential. So that's pretty great, because it means our simple algorithm, it's actually a reasonable algorithm. It's not a stupid algorithm. It's not the most efficient, but it's not stupid. And now look, let's try to improve it. And in order to improve it, well, there's a vast literature of sorting algorithms. We're not going to go into it too much. We're just going to look at one of the classics of the genre, the Mergesort algorithm. So before we do that, let's look at the sort and just have some kind of a, if we can intuitively express a completely informal and intuitive opinion. Why do you think this algorithm could be improved? What's inefficient about it? Do you have any opinions about it? You can, yeah. Yeah, it seems to go. It seems to go through things several times. Yeah. Yes. It is here, yes.
Thank you.
Yeah, and particularly two functions that go over the same data with apparently no good reason are filtering followed by append. So filter and append go over the data twice in order to, which it looks like it could be made more compact. And that's exactly what Mergesort is going to do. So I have it pre-implemented here. Mergesort. So what's the idea of Mergesort? The idea of Mergesort is that I start with a list like this, and then I split it in two. Yeah? I don't try to split it into the elements that are less than or greater than the head. I just try to split it into two equal parts. Yeah? So I split it, and by split it, I mean I create two lists that have the elements of this list, and they're as much as possible the same size. Now these ones, I sort recursively. So this is sorted, this is sorted. So I have two lists, but remember that list was just split arbitrarily in two equal sides. It was not split according to any criteria. So I cannot just concatenate them. What I have to do is merge them. So I write the function, and basically it's going to take one element from each list, and it's going to move always the smallest one to the head of the result and just carry on. And notice that I can do that in just one pass, whereas before I needed 2 passes over my list. Okay, and this is called merge sort. And both merge sort and the previous sort, let's call it simple-minded sort, are what's called divide and conquer algorithms. Divide and conquer. And these are very good algorithms because they tend to be the most efficient. It's when you can take your data, split it in two, solve it separately, and then put it back together. That's a divide and conquer algorithm. And that's a very good strategy when you can get away with it. So first of all, let's look at the functions that we need. So we had first, well, the comparison function just like before. It's going to use the difference and compare it with 0. Then the split function does this. And this is very simple, right? It just goes through the function. If it's empty, it's empty. If it has only one element, it's going to arbitrarily put it to the left. But now if it has more than 2 elements, then it's going to call itself recursively and put the first one into the first result and the second one into the second result. Yeah? Recursively is going to create these 2 lists. So basically, just to give you a clearer idea, the first element is going to go here. The second element is going to go here. The third element is going to go here. The fourth element is going to go here, and so on. So it's kind of it's an unzipping of the list in 2 lists rather than in a chopping. You cannot really, it's not very convenient to chop a list in 2 because you don't know where the half point is. And now, the function that does the hard work is the merging, this function. So what does it do? Well, if it's empty, it's merged. If it has only one element, it's merged. Otherwise, so first we split it. Oh, sorry, I'm here. So yeah, if it's to merge 2 lists, if one of them is empty, these are the first 2 cases, then of course merging is trivial. You just take the other one. Now if it's not, so if both lists are non-empty, then we compare x and y, and we take the smallest one, and then we merge the rest. Yeah? So we always look at the head, we take the smallest one, and we put it here, then we repeat. And yeah, so that does. And finally, now the merge sort is the overall process. We start with a list. We split it into a pairs of lists, which we call L for left and R for right. We sort L prime. We sort L and we put the result in L prime. We sort R and we put the result in R prime. And then we merge L prime and R prime. And that's the merge sort. Now, can you tell what is unusual about this function compared to the functions that we have seen so far? What's unusual about the pattern of recursion in this function? Yeah? Yeah, it's not, so this is not a structurally recursive function. It's a recursive function, but it's not structurally recursion. It's not defined in terms of the head and tail of the argument. And what this means is that we don't have an easy guarantee that this function terminates. If you wanted to prove that this function is correct, you would need a separate method that we haven't studied yet, and we're not going to. We're not going to study how to actually prove that this terminates. So that's quite tricky. You have to show that it terminates. We're not going to. So in order to benchmark it, we do the same thing. We create a random list, we feed it with a random size, and then we run the profiler on a bunch of data, and then we put it in our spreadsheet, which I prepared ahead of time. And the only thing that they have in common now is the number of comparisons, because internally, so here, the previous function, it had append, filter, and so on. But now we don't have append and filter. The only thing that they have in common is the numbers of comparisons. How many comparisons they make. And we can just compare. So for 10, 44 versus 23. For 10, 20, and so on. So if you put in normal linear coordinates, you can see that Mergesort is here, and naive sort, or simple-minded sort, whatever, is here. So it uses, and it seems to grow a lot faster. Yeah, so obviously, according to these data, Mergesort is going to be more efficient. It does a lot less comparison. And if you set it on, and it's by quite a lot. So here it's the order of 200,000, and here is on the order of 4 million. So at this level, at the level of a list of a list of only 20,000 elements, the difference is about 20 times or so. So if this is going to take 1 second, this is going to take 20 seconds. It's quite significant. And this, as you can see, the gap between them is only going to grow as the lists get bigger. But if we want to look at the orders of magnitude it takes, and this is the logarithmic scale, then in terms of order of magnitudes, then you can see that the difference is no longer that much. So order of magnitude means that if one of them is going to take days, the other one is going to take also days, but just more days. But it's not going to be one is going to take days, the other one is going to take millennia. So they are going to be roughly within the same orders of magnitude. And I think without knowing a lot of theory about how to do things, that's an easy way in which you can yourself benchmark your programs and also estimate whether you're improving it or not. Profile it, try it on various sizes of input data, and then try to see what are the trends. Linear, sublinear, which is great, superlinear, which is not so great, but just make sure it's not exponential. Exponential is a disaster. Okay? So, and then there's another thing that I wanted to say about Mergesort, and that's going to be, hope, quite fun, is that Mergesort is not just a potentially efficient algorithm, but it's also an algorithm that can be done in principle, not by OCaml, but by other programming languages and other systems. It can also be done in parallel. Yeah, because you see here, when you're sorting, when you're breaking the list in two, sorting this side and sorting that side can be done independently. There's no interaction between them. So if you had more than one processor, then you can do it. Okay. So I want to see now, if you are the computer, the class is my network of computers. We're going to see if you can sort a deck of cards in parallel using the Mergesort algorithm. So how does it go? I'm going to give the cards, the pack of cards, to somebody in front, and then that person is going to split it in two. This is going to be the first step. And then he's going to pass it to two other people or two other processors. And you have to remember who you passed it to. And then they're going to do the same until it's going to go down to one person who's just going to have two cards or three cards. And then those cards, he's just going to sort them themselves. So if you have an 8, a 9, and a 10, you're just going to sort it. And then you're going to give it back to the people who give it to you. And then that's where the difficult part is. You have to do the merging. So you are going to get two piles of cards which are already sorted, and you put them like this. You put them like this, face up, and you always select the smallest one and you put it face down. You look at them, you select the smallest one, you put it face down. Always like this, and when you're done, you pass it back to the person who gave it to you. Now, it's important that you only get involved once. So even if somebody gives you a card, then don't accept another card again from anybody else. Because when they're going to come back to you, it's going to be confusing. And try to spread as wide as possible and then deep so that you don't run into dead ends. Okay? So I'm going to set up a competition between the right sides. So I'm going to start in two places. Wait a second. I'm going to start at this corner so you can spread like this, and I'm going to start in that corner so you can spread like this, and they'll go back. Now the people who are the first ones, they're going to have to do the most work because they have to join. They have to do the final join. So you're a bit too isolated. I'm not going to start with you. I'm going to start with Turkey. Don't start just yet. Wait. Hold on. Don't cheat. Okay? So, you try to split it into two equal parts. You pass it along. When you have three cards or less, just sort them and pass them back. When you get back, you have to get back two packs and merge them properly. Okay? Go! Hey, what? You just split them and you pass them. What are you doing? Do you understand how it works? You split them and you give them. You only sort them when they come back to you. You just split them in two equal parts and you pass them along to two other people. Ace is highest.
up to